All right, welcome. So today I'm going to be discussing the development of a Wald-type statistical test to compare live test data with M&S predictions. So the central question that we're trying to answer with this is, what methods can researchers use to ensure that M&S predictions actually agree with live test data, and how can this methodology be standardized? So for some background, we're doing this work in collaboration with the Centric Weapons Analysis Facility, or the ECWAF. This facility is operated by the Naval Undersea Warfare Center, or NUWC, as a hardware-in-the-loop, real-time Mark 48 torpedo simulation facility for operational testing. So that's a mouthful, but how it works is it tests torpedoes via modeling and simulation by taking over there, you can see kind of the brains or the torpedo processor, pulling it out and connecting it to a bunch of inputs and outputs. So it can then feed in simulated test conditions and as an output receives what the torpedo thinks it's doing in the water. So testing like this has a lot of advantages. It's much more cost effective than going out into the ocean and shooting a bunch of torpedoes. And it also allows for testing novel environmental and adversarial conditions that you just can't get out in the ocean. However, as with any M&S, there's the risk that this might not be producing accurate results. And so to that end, IDA is working on the verification, validation, and accreditation process to confirm that this facility is doing what they say they're doing. So how do you evaluate results from a torpedo test? One way to do it is by making a bunch of logistic regressions. We're interested in a binary response variable, whether or not the torpedo hits the target. But that can depend on a lot of different factors, such as the environment, like the ocean depth, whether or not the target is employing countermeasures, anything like that. So these plots here are, this is all fake data. Unfortunately, I can't show you the real data, but this is illustrative plots. Say on the left, we have a logistic regression obtained from live test data out in the water. And on the right, we have a logistic regression from this ECWAF data. So the question then becomes, are these models created on the same set of underlying data, and how can we know? We're interested in whether the models have the same output response, but also the coefficients of each of these environmental variables, because we want to make sure that the ECWAF is accurately modeling all of these environmental conditions. If it's not, that means that something is probably incorrect in its logic and should be revisited before it can be used to test further conditions. So to do this comparison, we turn to a class of statistical tests called Wald tests. The formulation of a Wald test is up here on the slide. I'm not even trying to get the pointer working, but essentially how we do it is we take the coefficients from these two logistic regression models, and for each pair of coefficients, simulated and live data, we take the difference, normalized by the covariance matrix, and we get a test statistic. So this test statistics allows us to look at the null hypothesis, which is that the simulations and the live test data do agree, versus the alternative, they don't agree. And one cool thing about this test statistic is that it follows a chi-squared distribution. So for those of you who know stats, you know that means that we can get p-values from this and therefore choose whether or not to reject this null hypothesis. So this seems easy, but what happens if you have some variables that are estimable in one model but not in the other? So as an example, consider you're going out into the ocean and doing a bunch of live test data with a target that is employing some kind of active countermeasure. So you get results from that. Your logistic regression model is not going to include a coefficient for these countermeasures because they were always there. It doesn't know anything about what happens when they're not countermeasures. However, let's say for the ECWAF, you have a bunch of runs both with and without countermeasures. So you're going to get this countermeasure coefficient. So the Wald test requires all of the coefficients to be matched evenly across the two. So what do you do with this? You could just throw out all of the ECWAF runs that don't have countermeasures, but then you're losing a lot of useful data. That's not the best solution. So instead, we look at the framework of generalized linear models, of which logistic regression is a type, to figure out what to do. So getting into the interpretability of this live test data model, we have the model's response depends on this intercept term that represents the model's predictions with countermeasures at a depth of 0. And then you have other terms, for example, a depth term that changes this prediction based on changing depth. So again, this is with countermeasures because all of your live test data was done with countermeasures. However, for your ECWAF data, your intercept actually means something a little bit different. This time, it represents the model's prediction without countermeasures at this depth of 0. And you have this additional term that adjusts this prediction if you do have countermeasures present. So the way to deal with this is to just reformulate this intercept term in the second model. You basically add the coefficient describing countermeasures to the intercept term, and now you have a new intercept that describes the model's predictions with countermeasures at a depth of 0. Now we can compare this intercept term with the intercept term from our live model, run the Wald test, everything is good. So that is the algorithm that we applied to generate this robust Wald test in R. We identified all of these mismatched coefficients, things that were present in one of the models but not in the other. We then found the fixed value for that corresponding coefficient. So in this example, the fixed value was 1 because countermeasures were always present. If you had, for example, a bunch of live tests run at the same depth, your fixed value would be that depth. You then multiply these mismatched coefficients by these fixed values, which gives you a number, and you add that number to your intercept term for that model. If you do that with all of these mismatched coefficients, you then get two models that are encoding the same information for the data that you have, but whose coefficients match up 1-to-1, so you can run this comparison. We then perform a similar operation to adjust the covariance matrix because, once again, we have to merge the mismatched rows in with the intercept rows in order to make the Wald test run successfully. And so we do all that, and the output is something in R that looks like this. So once again, this is all fake data. Don't read too much into this, but you simply have your result. You call the Wald coefficient compare function on your two models that you created, model 1 and model 2. And your output gives you a test statistic and a p-value. And with this p-value, you can interpret this and choose whether or not you would like to reject your null hypothesis. So we actually did run this test on the real set of ECWAF and live torpedo test data. And we did not find any meaningful differences between the MNS and the live data. This is evidence that the ECWAF is working well for the limited range of test conditions for which we tested, but we still need to run more testing to figure out if it's actually working in all conditions across the board. That is all that I have.